of really understanding the problems is just figuring out what the question's asking, more than anything else. So let's take a look at 20 to start off with. Let's see. Here it is. They're asking a question in a different way. All right, so this says, let capital f of x equal the definite integral from 0 to x of f of t dt, where f is the function, little f is the function below. So here we have little f of t. And capital F of x is the definite integral of what we're looking at. All right? Another way of thinking about it is capital F of x is the area function. How much area do you have? So let's just do let's do a quick example. If x is 0, what is capital F of x? It is. How'd you get it? Capital F of x would be the area from 0 to 0. X is that upper limit of integration. Okay? When x is 2, what's capital F of x when x is 2? And again, remember, capital F of x is the area function. So take a second, think about it, look at the picture, think if there's anything you can do that will help you with that. So f of 2, capital F of 2, is going to be equal to the definite integral from 0 to 2 of f of t dt, where there's f of t is this function here. Derek, thoughts or ideas? Kaylee, thought or idea? Okay. So you can count blocks. You're going to go with somewhere around 3 maybe? All right. I bet you it's just a little bit more. I think it's like point... Okay, fine. Actually, if I wanted to find the area of this, what kind of shape is that looking like?
Quarter of a circle.
Quarter of a circle, so 1/4 pi r squared, where r is 2. We get around pi. Okay. What about when x is 4? 2 pi? All right. What about when x is 6? What starts to happen to the area function when we go from 4 to 6? Yeah, but what... negative. So the area function starts to decrease. All right, so it's at 2 pi minus 1. Okay, so, hey, you know what this is? This is the same thing as asking the question, hey, this is the derivative, right? This is the derivative of f of x, I'll use another letter. The derivative of little g of x. Tell me some information about g of x, right? So if this is the derivative, this says g of x increases from 0 to 4. Not only that, it tells us exactly how much it increases, right? From 0 to 2, it increases by pi. From 0 to 4, it increases 2 pi. So here's just another way of asking the same question we've been asking before. So if capital F of x is the area function, and you're looking at what we're taking the area of, it's just like saying, you're looking at the derivative, talk to me about the function. Is that all right?
That makes sense, yeah.
It's a little hard. I mean, it's definitely a different way of asking it, and it's hard to sort of wrap your mind around the fact that, okay, the area function, oh, well, that's just the definite integral of the function. Well, what's the definite integral of a derivative tell you? The definite integral of a derivative tells you about the function. But wait, I thought f of t was the function. Well, it is, but we're taking the definite integral, and now we're talking about capital F of x. Like, it's just like, we're really just changing the names of the functions that we're calling. So, all right, now that we understand the question, and what intervals is f increasing? Be careful. And you can actually think about this first or second semester. You choose. Gabby, you want to tell me when you think capital F of X would be increasing?
From 0 to 4.
That's definitely one interval.
8.
Okay. And if you did parentheses, that would be fine too. I'm going to use brackets. Definitely. As a matter of fact, that's exactly where little f of t is positive.
Yeah, why?
Thanks. Sorry, I don't know why. Is that better? That's better. Okay. So in other words, f is the derivative. F is the function, and we're looking at the derivative. Awesome job, Gabby. All right. Let's see. Let's try B. From 0 to 8, Gabby Collinswood, where does it hit a minimum, and can we figure out what that minimum value is? Go ahead, tell me. What? What's the value at 0? Oh, f of 0 actually equals 0. Where's another place where there's another minimum? At 6? And f of 6 we already figured out is what? 2 pi minus 1. Which one's less? 0. So actually, if we want to find the minimum value, it's at 0. And I think a lot of people would have overlooked that, Zach. All right. How about D? Skip C for a second. How about D? When is capital F concave up or concave down? So let's just start, when is it concave up? Thoughts or ideas on that? Derek?
0 to 2.
You can even do better than that. All right, so let's see. 0 to 2, 5 to 8, because those are places where the derivative is, and as a matter of fact, instead of saying 0 to 2, how about
You could even do negative 3 to 2.
negative 3 to 2? Okay. And where are the inflection points? How does that tie together? Inflection points happen when the derivative does what?
Equals 0.
Not when the derivative equals 0. Derivative equals 0 is when the function has mins or maxes. When is it what?
When it changes sign. Or when it changes direction, it's increase to decrease. So
All right.
At x equals 2.
2.
And x equals 5. Yeah.
So when the derivative has minimums or maximums, that's when there's a point of inflection, and that's when there's a change in concavity. Okay? So when the derivative stops increasing and goes to decreasing, that's a point of inflection. And when it stops decreasing and goes to increasing. And so those are mins and maxes of the first derivative. Does that seem sort of familiar from first semester?
Mm-hmm.
Right? Do you see how it's sort of we're just going backward? You can look at it two ways. All right? You can look at it first semester, or you can look at it second semester. That was hard. Do you want to ask any questions? We'll do more practice, but was anything unclear or ambiguous or just downright tough? AC, all right? Adrian? Jack? Okay. All right. Let's see. Oh, 21's fun because you don't have to do any work. So 21's asking the same question in the same way. Let capital F of X be the area function. Which of the following could be a graph of capital F? And obviously we're going to have a discussion about this, right? Zach, what are your thoughts? Is there A, B's, and C's? No, there's not. Can we just call this? Let's call it A, B, and C. All right, what are you going with? I want you to give me a reason why C can't be right. Uh-huh. Kaylee?
No, a reason for C is that the function is always positive, so it has to always be increasing.
All right, so this function, little f, is always positive, which means we're always adding area, right? Whatever you do, you're always going to be adding area. So Kaylee says, well, if you're adding area, that means you're always increasing. Or the first semester view of it is, hey, this is the derivative and it's positive. If the derivative is positive, you're always increasing. All right, C's gone. All right, we have A and we have B. They look very similar to me. I don't know. Let's try if we can do the right answer. I think it's going to have everything to do. Well, I don't know. Maybe I'll be quiet. Will, is that a hand?
A.
Why A and not B? Jack, you agree with A?
I agree.
All right.
Because if the original thing is the derivative.
Okay, so Will's saying, hey, instead of thinking about this as little f of t, let's think about this as the derivative of big F of x.
Then you're going to know that if there's like an actual rule for this, but if it has like one diff, the original function is going to have two, so there's one less.
All right, so the derivative should be 1 degree less, and so you're saying this is sort of like an x squared thing, so you're thinking the function should be sort of like an x cubed thing? All right, that's a good way of thinking about it. The function's always going to be 1 degree more than the derivative. All right. Something to further add to that?
Yeah, I didn't think of that, Mike, but that does help a lot. I just looked at the derivative, so the first graph, and I realized from 0 to 1 it's decreasing, but it's still more from 1 to 2. So I just kind of did like step by step, saw how much the function was increasing.
All right.
And realized that it from 0 to 1 increases like 18, and then it decreases a little bit from 1 to 2.
It doesn't. It still increases, but it increases by a little.
It's decreasing.
Ah, all right. Which actually means, look, Jack's saying from 0 to like around 2, the derivative's decreasing, which means the function should be slightly concave down. Right? And then the derivative's increasing, which means the function should be concave up. And that's really what we have there. So it's another way of looking at it. That's nice. Good. Wow, I'm impressed. All right. Let's do maybe 1 or 2 of these. This is going to be hard. Yeah, let's see if we can do like 22. Maybe we'll try A. Maybe we'll try A and maybe D. All right, so, hey, there it is, asking the question in the same exact way about the area function. And it says you're looking at the function f of x. It seems to me that really what that question is saying is, hey, you're looking at what?
The derivative.
Okay, you're looking at the derivative. Can you draw the function? That's what it's asking. This is going to be hard. How about, let me give you like 20, 30 seconds, like do a little sketching, then we'll talk, like you can check with someone next to you, like, we'll do A. I think we'll do A.
Are they always A?
Yeah, so Zach says, hey, it says A of 0 equals 0, and that might be important, right? That might be important at some point, and I agree. All right, let's take a look. What can you tell me about A? There are things that we can say, and then we're going to maybe try to get more and more exact. Gabby, what can you tell me about A?
You know, the slope of the line is 2.
All right. Oh. Up 1. Okay, so you're saying this slope always has... Actually, this is the graph of 1/2 x. The slope is always 1/2. All right. How can we add to that? Enhance it? Do something different? What do you want to do with that, Asa?
Well, the zero of the function, or of the derivative, is at x equals 2.
Okay.
And that serves some significance to the integral, or the function before that, I guess, because that's serving either as a minimum or maximum.
Which one?
It would be a minimum.
Why? You're right.
Because when the when the derivative goes from negative to positive,
Right.
the function goes from decreasing to increasing.
All right, so this is going to be a minimum at 2. So if I'm going to think about dividing up my function into zones. I know over here, Asa says the derivative's negative, so that means the function is going to be decreasing. And over here, the derivative is positive, so my function is going to be increasing. All right. Add a little bit more. Gabby and Asa each gave us some pieces to it. What else do you have? Go ahead.
Alright, well, we can find out the integral from 0 to 2.
All right, so from 0 to 2, we know we're going to decrease. Not only that, we know we're going to decrease by exactly 1 unit. So if we start at 0, 0, which we have to, and we decrease by 1, by the time we get to 2, I guess 2 comma negative 1 has to be a point.
Yeah.
All right. It looks like between Gabby, Asa, and Jack, we're really starting to piece this together. Gabby, you want to...
I don't know if this is going to find an integral, but you know, like, the y-intercept's -1, like, the equation. So there's 1/2 x.
All right. This is going to be very interesting. All right. All right. What do I want to say?
The function.
All right. So wait, what else do we have? Zach, did you have a thought or idea? I know you did because your hand was up a little earlier. I think so. Okay.
Because
So,
because it's a linear function, the degree has to be 1 more
all right.
than that if it's going to be an integral.
So this is back to what Will said. You guys are doing a great job at listening and picking up on what everyone's saying. That's good. So from 2 to 4, the function is going to increase by how much? 1. And from 4 to 5, it looks like it's going to increase by, I don't know, maybe another 1. Maybe a little more than 1. So maybe we're going to have something like this. What do you think the function is? Gabby's given us so many lots of like little pieces that we could like start piecing together. What do you think that function is? Can you look at, like, Gabby gave us the derivative, right? She's actually saying the derivative is 1/2 x minus 1. Can you find out what the function is? Jack, you think you know? Well, go ahead.
Will the function be y equals square root x minus x?
Root x. So that would be, you're saying x to the 1/2?
Yeah, and then
Minus x.
Yeah.
All right, so let's see. I agree that the derivative of minus x is going to be -1. But the derivative of x to the 1/2 is going to be 1/2 x to the -1/2.
So it would just be
All right.
0.5x.
No, that's wrong.
No.
1/4.
1/4 x squared.
Like,
Is that going to work?
Yeah, that is, because I'm
1/2.
going to multiply 2 by 1/4 to get 1/2 and get the 2 out of the way.
Awesome. That's great. That's impressive. Look at what you did. You just looked at the derivative and you figured out what the function was. That's awesome. You did it algebraically and you did it with a graph. Wow, that's impressive. Can we just look at this for one more second? So we know from 0 to 2, it drops by 1. What about from 0 to -2?
Well, it's a trapezoid.
Drops by 1.
From 0 to -2?
No, it drops by
What's the area from 0 to -2?
1,
3. It's below the x-axis.
So it'd be
-3. But we're integrating backward. Yeah. since we integrated from 0 to negative 2, that says if I want to go from 0 to negative 2, right, I have to go up 3. So my graph wasn't totally right. It should look something more like this. Whoops, I thought I just drew it. So do you understand how from 0 to negative 2, if we integrate backward, that says go up 3 units. If we integrate from negative 2 to 0, we go down 3 units. So if you integrate forward from negative 2 to 0, drop by 3. If you integrate backward from 0 to negative 2, go up by 3. Is that all right? That was hard because it's a double negative, right? It's negative area, so if we go backward, it's going to be an increase. If it's negative area and we go integrate from right to left, it's going to be a decrease. Sorry, from left to right, it's going to be a decrease. Let's do D, and then Zach's saying it's time to go. It's almost nap time. All right. Huh. That's a weird graph. Well, we know A of 0 is 0. What's the slope? What do you want to think of them as? Sure. Now, you'll tell me that from 0 to 3, the function is... What? No, 0 to 3. If we're looking at the derivative, from 0 to 3, the function should increase. All right? The thing about thinking about them as the area function is you can say not only increase, but you can tell me exactly how much to increase. So from, let's say from 0 to 1, how much should I increase?
3.
All right. From 1 to 2, how much should I increase? 3. Oh my gosh, I'm running out of room. From 2 to 3, how much should I increase?
1.
All right, so that's 1.5. So that's up here. So I think I was going straight, and then I sort of leveled off. And then from 3 to 4, how much should I decrease? Another 1.5. And then from 4 to 5, I should decrease by 3, right? Now, that looks like a parabola, but it's not really. It's really a straight line with a little parabolic bump at the end, and then another straight line. Sorry, I don't know why it's freaking out like that. And I guess... and I guess from, let's see, from 0 to negative 1, it's positive area, but I'm going backward. So I actually have to go down 1.5. But if you look at the story from negative 1's perspective, negative 1 is saying we're going to go up, we're going to increase to 0. So do you see how looking backward is sort of like, I don't know what I want to say. It's a different story that says the same thing.
It's like the friends that are going.
It's going right down is the same as going left up. Right? Going right and down is the same as going to the left and up. No, that's not true at all. Wait, how do I want to say that? I don't know.
Up is the same as going right down.
No, that's wrong. I don't know what I don't know what I want to say. All right. That's good. You did an awesome job. I'm impressed. Very impressed.